Welcome back. We're in lesson 11. I hope you guys have plenty of paper because this is going to be a long one. We only have 3 example problems, but we're going to be covering some new material in the second part that you're going to need to draw a lot of shapes for. So let's get started. We're going to talk about the addition of fractions and refresh our memory on that. We know that if we have fractions with the same denominator, like this one, they all have the same denominator, we can put them all over the same, we could perform the operations given, which could look like something like this. We could put them all over the same denominator, just like that, and end up with our answer of 2 over 11. It's the same thing, right? So these are all the same thing. So we're going to do that with variables as well. And we can do that with variables. If we have an expression that is a over b plus 2 over b plus a plus 3 over b, we know that we can put all of that over b because it's the same denominator, and that it would equal a plus 2 plus a plus 3 all over b, which would then equal 2a plus 5 over b. My pen is messing up again. I meant to change the tip since the last lesson, but I did not. 2a plus 5 over b. So it's the same thing. You see how that works. We draw that correlation. As long as the denominators are the same, we can condense them, right? So that's what we're going to do in example 11.1. I'm going to keep that in mind as we do this problem. So our problem is this right here. You can take a moment and write it down as I write it down. All right, so here's our problem. Now, unfortunately, we do not have the same denominator under each one of these fractions. So we need to find the least common multiple of the denominators of these fractions. And the way we do that is we find the greatest degree of all of the factors. And in that case, we've got a constant of 2. Then we have a to the first power in everything, but then our x goes as high as x to the third power. So that's the one we're going to use. And that's how you find the least common multiple, right? So that is what we're going to use and multiply times what's up here in order to find, in order to get everything to be a common denominator. So we're going to start with this, and all you're going to do is you're going to look at what this fraction has as a denominator and multiply the numerator by what it's missing. So in this case, it has 2a. It doesn't have x cubed. So we multiply k times x cubed. So we just write kx cubed because that's multiplied by x cubed. And we move on to the next fraction. This has ax squared. So the only thing it's missing is a 2 and an x. So we say 2x times bc, and then we move on to the m. And m, the only thing that's missing here is the 2. So we say 2m. And we put all of that over our common denominator, 2ax cubed. And then we are able to do whatever math we can do. Now for 2x bc, the only thing I can really do for this is write it like I should have written it in the first place, 2 x bc without the parenthesis. I had to look at my denominator for a minute and see how many x's I needed. And that's it. That's as far as we can go with this answer. we have kx3 plus 2x bc minus 2m all over 2ax, and that's a 3 right there. Let me make that clearer. All right. So that's 11.1. 11.2, let's do it right here. And here's our problem. It's a little bit easier to see. It's a little bit shorter. We have m over k minus b plus cx all over, or that one's over, ak to the second power. Make sure that's a 2 right there. There we go. All right, so what do we have for a common denominator? Well, we have k here to the 1, and we have ak squared here, and then we have the number 1 here, because we can always put this over 1 and make it a fraction. So our common denominator is going to be what's under cx, because that is the highest for a and the highest for k, and there's always a 1 in front of a variable, so we can leave it just like this. So we're going to write everything over a k squared, and then we're going to multiply by whatever is missing from here. So m is going to be times, we have a k here, so we'll take one away. So that's going to be m a k. And now we're going to subtract, we're going to minus b, and there's nothing here, so it's going to be times the whole thing, b a k squared. And then we're going to add, and cx has all of it, ak squared, so we don't multiply by anything, so that's just going to be cx. And that is our final answer. All right, so you find the greatest or the least common multiple, which is going to be the greatest exponent value per base, and the constants. If you have any constants, you just multiply them together. And then we multiply by the difference for each term. And that's our answer. All right, let's move forward. Now we're going to talk about something that we did not talk about last year in Algebra 1, if you were in my Algebra 1 class. Pause if you need to take notes. I'm about to clear the page. All right, so we're going to talk about inscribed angles. An inscribed angle is an angle that is within a circle. Let me see if I could draw a circle. Not really, apparently. Come on, I don't want that. I want an actual circle. Let's see if I could do better this time. All right, there's a circle. Let's make it a little bit bigger so we can see what we're talking about. I'll move it down. All right, here we go. An inscribed angle. So let's find the center of this circle. That may or may not be it. Let's pretend that's it. So we have a line here, and we have a line here. And let's just pretend we know exactly where, what this is. This is, we'll say it's 44. Let me get my pen. This is 44 degrees, this arc right here. All right, from this point to this point, it's 44 degrees. And if your degree of the arc, your inscribed circle stops in the center of the circle, then the measure of your angle of the inscribed angle is also 44 degrees. I think we talked about that already. So that's 44 degrees inside and 44 degrees of the circumference of your circle. However, I'm going to change colors. If you take that same measure, or those same points, that 44 degrees, and you go all the way to the other side of the circle, to the outer edge, then this degree of measure becomes half of the inscribed arc. So that's going to end up being 22 degrees. Okay, and it doesn't matter where it hits, as long as it's on the outside edge, it's going to always be half of whatever this is, or whatever this is. These two will be the same. When it goes all the way across, it's going to be half. Okay? So you might want to draw that illustration so that you can put it in your notebook. And remember that. All right, so what if we have a full inscribed circle or inscribed triangle here? What if we have a right triangle inside of our circle? Okay. The endpoints of a diameter of a circle intercept an arc whose measure is 180. What that means is we have a diameter. That's what a inscribed circle of 180 is going to be, because it's going to go through the center of your circle. That's going to be the diameter. When you have two radii or a radius that they line up, that is your diameter. And at any point that you have a diameter as one side of your inscribed circle, then your inscribed triangle or your inscribed angle directly across from the diameter becomes the hypotenuse, and this becomes a 90-degree angle here. Okay? And it doesn't matter whether you draw it here. Let me get a different color and I'll show you. You could draw that here. Well, if you could draw a straight line, you could draw it here. So let me draw from here to here. Okay, and then from here to here. This is still a 90-degree angle. So it doesn't matter if your diameter is the one side of your triangle on the inside of your circle, that becomes the hypotenuse, and the opposite angle is going to be 90 degrees. All right, you can write that down as fact. That you can draw this as an illustration as well. So if the diameter is, let me get my pen, let me erase this. If the diameter is a side, it becomes a hypotenuse. And we know that a hypotenuse is across from a 90-degree angle. All right? We know that to be true, and we also know it to be true that if it comes to the center, it is the same degree of measure as the arc on the outside. And if it goes all the way across from that arc, it is going to be half of the degree of measure of the arc. Okay? So those things are true. Please write this down in your notebook. You are going to need this for future reference because we are going to be doing some problems using inscribed circles. I'm going to clear the page, so pause and take notes if you don't have this down yet. All right, continuing on in inscribed circles, we have another example for you. Another circle up here. All right, very good. So now, if we have our diameter, right? Here's our center. If we have the diameter, first let me back up. In a later lesson, we're going to prove about the measure of an inscribed angle. We're going to prove that equals half the measure of the intercepted arc. That's okay. For now, we're just going to content ourselves with the illustration that uses the numbers. We're just going to depend on it, that it is a fact, and we'll prove it later. Right now, we will begin with this. So let's say we have a diameter here, and we have a radius, another radius here, that connects a line here. So this becomes an inscribed angle from this point. all the way around to this point. It's not a very good line, is it? All right, from this point here all the way, that's a little bit better, to here, we found the degree of measure for that, and that ended up being, let me mark it, that's an 80-degree intercepted arc, right? That is the degree of measure here, which means that that is the degree of measure here. That's 80 degrees, by the way. Make that a bigger circle. So if this is 80 degrees and this is a diameter, then we know that the degree of measure here is 100 degrees, right? Right. And we know that because this is a radius and this is a radius, that these two are the same length, which makes this an isosceles triangle. And if this is an isosceles triangle and these two are the same length, then these two angles here are going to be the same measure, which means 180 minus 100 means that it'll be 80 divided by 2 to get the measure of these two. So these two are going to be 40 each. So whatever this inscribed or intercepted arc is the degree measure here. And because it's a diameter, it's a straight angle, which measures 180. So 180 minus whatever this degree of measure is the degree of measure here. And if this is a radius and this is a radius, they're equal in length. So we take whatever degree of measure is left, 180 minus whatever this is, and divide it by 2. And that's going to be our two congruent angles on the end of our isosceles triangle. Do we see? All right, if you hear some like weird noise in the background, that's my dog, he's snoring. All right, so that is what we have here. Now, don't depend on my drawing skills. This looks more like a 90-degree angle than an 80-degree angle, but I'm going by what the book has for their measurements. So keep that in mind when you're looking at shapes within a circle. This is going to be 180 degrees. So if you are given this degree of measure, and we know that that's going to be equal to the degree of measure to the radius, then you know what the other degree of measure is on the opposite, on the exterior angle here, or the other angle. And because this is a radius and this is a radius, it's an isosceles triangle, so you subtract this from 180 and you divide that by 2, and that gives you the congruent angles here for this triangle angles of measure. All right, so I hope that you could take all this down. If you need to pause and write it down, put that in your notes. Please, please, please do that. I'm going to mark this is a radius, this is a radius, this is a radius, okay, for your further illustration. All right, that's all I have for lesson 11. Spend some time looking over your notes, maybe re-watching this on Inscribed Angles within a circle, because you will have some problems. Oh, I was about to let you go. We have one practice problem for this. It's 11.3. Let me draw a circle for us. Depend on the numbers, not my scale drawings, because the numbers are the parts that you need to know. All right, so we have an angle here inscribed inside this circle. Let me make this a little bit bigger. Here we go. So that, and then a little bit larger right there. Okay, so this is a 40-degree angle. Where's my pen? Let me redo that. Now we can write it. This is a 40-degree angle right here. All right, I'm going to make sure this goes to where it's supposed to go. It's supposed to touch right there. All right, okay, done. All right, so we have a 40-degree angle that's inscribed in this circle. And we have two measures here and here. Now we need to find x. The measure from here to here is 7x plus 40. And the measure from here to here is 5x. Now, taking what we know about inscribed angles, we should be able to find what x is. We need to find x. And I'm going to walk you through it. Okay, so if this is 40 and it's all the way across, then we know that it is half of this inscribed arc right here, this intercepted arc. I keep calling it inscribed. The angle is inscribed, the arc is intercepted. So the intercepted arc is twice this. So that means this is going to be 80 right here, right? You follow? All right, so if this is 80 and a circle has 360 degrees, then we could subtract 80 from 360, and we are left with 280, right? So the whole rest of the circle should be 280. So that means that this plus this should be 280. So we can add them together. We could say 7x plus 40 plus 5x equals 280. So now we can combine, and we could say 12x, and let's go ahead and swap this over and say 280 minus 40. Okay, so that means 12x equals 240. So x is going to equal 20. And according to my book, that is correct. So you see how we got that? We remembered that an inscribed angle, when it comes to the diameter, it's the same measure as this. But when it comes all the way to the other side of the circle, it's going to be half. So we doubled this to find out what this intercepted arc degree was, and that was 80. We subtracted 80 from the full degree. Remember, a straight angle, the diameter is going to be 180, so that's only half. The full degree is 360. So we subtracted 80 from 360 to take out this portion that wasn't included. And then 280 is what this plus this had to equal. And then we just solved for x. All right, so go back and watch the video again if you need to think that through. And that is all we have left, or that's all I have for lesson 11. I will see you in lesson 12.